Swayam Prabha. Digital India. Educated India.
Welcome to this lecture on transition metal organometallic chemistry from principles to applications. We have been covering a very important topic in this lecture, the last two lectures, that is about transition metal carbine complexes. These transition metal carbine complexes are transition metal bonded to Cr moiety, where the carbon is sp hybridized and multiply bonded. So, as a result, there exist three types of bond between the transition metal and the carbine moiety, which is sigma, pi and pi type interactions. These are called carbine complexes. Now, carbine complexes are sort of an extension of transition metal carbene complexes, which we had discussed in our earlier lecture, where transition metal is bonded to a carbene moiety and where the carbon is CsP2 hybridized, and these are called carbene complexes. And here too there is a multiple bond that exists between the carbene and the transition metal, which is a sigma and as well as pi bond. So, we see that transition metal carbine complexes are somewhat an extension of transition metal carbene complexes, and however, their properties are starkly different, and that we are going to sort of take a look and study them in more details. For example, transition metal carbine complexes more pi acidic than usually a very pi acidic ligand called CO. So, these are more pi acidic than carbine complexes, whereas carbene complexes are not as pi acidic as carbon monoxides. So, we see that even though these are sort of related to that of carbene complexes, however, their properties are supposedly very different. Now, in regard to this, we have looked into various preparative methods that are prevalent for transition metal carbine complexes, and the first and the foremost method was a serendipitous discovery for the synthesis of carbine complexes that sort of started off from transition metal from a Fischer carbene complex, which is over here. A reaction with BX3 reagent, where M equals chromium, molybdenum, tungsten, X equals chlorine, bromine, iodide, R equals methyl, ethyl and phenyl, which when treated with that yielded the carbine complex, which is X this is the carbine complex. Instead of a complex which was initially thought that it would give, and that the expected product was are which was never obtained. Now, if we sort of analyze this development of the synthesis of the carbyne complexes, what comes into fore? This carbyne complex was indeed obtained from a carbene complex. So, the first method, which is a serendipitous discovery for making the carbyne complex, was indeed initiated from the carbene complex, which got transformed to the carbyne complex. So, that is an important observation, because what it says that you already have a multiply bonded carbon transition metal framework in place, and then if you find another mechanism of forming an additional multiple bond, then you will end up in making metal carbyne complex. So, this is sort of something which emerges out of this serendipitous discovery of making carbyne from Fischer carbene complex. So, with this background, we are going to take a look at some other synthetic routes which have been explored and figured out for synthesis of transition metal carbyne complexes, and look at those preparative details with respect to what we had already covered for transition metal carbene complexes, and draw a parallel between these two classes of complexes in terms of the synthesis strategies that are in place for making them. So, similar to what we had seen for making transition metal carbene complexes, that alpha deprotonation provides an efficient method for synthesizing transition metal carbyne complexes. So, alpha deprotonation is an efficient method for synthesizing transition metal carbyne complexes. And here too we see that the transition metal carbyne complexes have been synthesized from the corresponding transition metal carbene complexes by alpha deprotonation. So, let me provide an example of the same. So, here is this carbene complex of tantalum, so this when reacts with PME3 with triphenyl phosphine CH2. So, what happens is that these proton gets deprotonated, and then it produces this PH3 CH3 cation and chlorine anion, which is eliminated. This chlorine anion is eliminated from here. So, basically this PPH3 CH2 abstracts this proton with the elimination of the chloride to give this PPH3 CH3 chloride salt, and along with that carbyne complexes are formed as shown over here. And the role of PME3 lies in the filling of the coordination sphere which remain vacant because of elimination of the chloride and formation of the carbine complexes. So, it sort of forms dative bond in whatever vacant site that is produced. This was again a method which was originally reported by Schrock way back in 1978. So, like the Fischer who himself had reported synthesis for Fischer carbene to as well as Fischer carbine. Similarly, Schrock too had his own synthesis available for making Schrock carbene as well as Schrock carbine complexes. And here also we see the parallel existence of similar strategy, that we find that the carbine moiety is formed from the carbene moiety. So, like the Fischer synthesis of treating Fischer carbene with Lewis acids like BX3 resulted in carbine. Similarly, the Schrock strategy of taking Schrock carbene and treating that with PPH3 double bond CH2 in presence of PME3 yielded the Schrock carbine. So, this method is applicable to early transition metal in high oxidation state. So, it is also to be noted that alpha deprotonation technique was also available for preparing carbene transition metal carbene complexes, and the way it is also available to make transition metal carbine complexes. Similar to or on the foot of alpha deprotonation, alpha elimination also is an effective method for producing carbine complexes. An effective method for producing alpha carbon complexes, and here too we see that this method is applied to carbene complexes. Elimination applied to carbene complexes to get what is called transition metal carbine complexes. So, here is an example of the same when Cp star, tantalum, CME3 reacting with DMPE in presence of sodium amalgam, which is a reducing agent. Alpha elimination of this hydride, the alpha elimination of this hydride happens to give this dimethyl phosphinoethane carbine complexes of the Cp star ligand, which is tantalum hydride So, what happens is that these hydrogen sort of alpha eliminates to give this triple bond and tantalum hydride complex, and DMPEE is replaces the two bromide atom to chelate and use the suitable vacant spaces which have been created by this. This is a very interesting method for obtaining carbyne complexes. Here also what we see that alpha elimination has been achieved on a carbene complex to result in the formation of the carbyne complex. So, in this process the alpha hydrogen of alkylidene which is alpha hydrogen of alkylidene is transferred to metal atom which is tantalum. So, this alpha elimination is also an effective method for synthesis of carbene complexes, and what we see that the same can be used for synthesizing a carbyne complex, and this can has been achieved on a transition metal carbene complex. So, of the three strategies so far that we have seen for preparing the carbyne complexes, all use a transition metal carbene as a precursor, and depending on the various methods they apply, transition metal carbine complexes have been formed. So, let us take a look at some other examples that are prevalent for making these carbyne complexes, and one interesting reaction which we are going to take and talk about right now is this metathesis reaction. Now, this metathesis reaction is starkly different from other three strategies that we have discussed, by the fact that it does not start from a transition metal carbene moiety to construct the transition metal carbyne moiety. So, the starting precursor for this metathesis reaction is completely different, and it starts with these metal triple bond and converts them to metal carbon triple bond in transition metal alkyne moiety. So, the example of this reaction involves tungsten, tubate oxide, whole 3, that reacts with an alkynes where R is an alkyl to give 2 of whole 3 Str, and this reaction was also discovered by Schrock, and that speaks volumes of about Schrock's ability to synthesize these carbyne complexes by more than one method. And the first one was by alpha deprotonation, and the next one is by metathesis reactions. So, in that way Schrock was kind of ingenious in creating metal ligand multiple bonded compounds, particularly transition metal carbyne complexes, and this reaction was prepared at under very mild condition from hexa T butoxy ditungsten and alkynes under mild conditions. So, this reflects on the genius of that Stork was. He could find more than one methods, at least two methods that we have seen for preparing these transition metal carbine complexes, which are extremely difficult to prepare. So, there are other methods which also produces carbine, and this one is from reactive dihalocarbene complex. So, the reaction of PPH3 osmium, hydride, chloride and CO with HgCl3 whole 2 with that eliminates HgCl3 and PPH3 gives this osmium dichlorocarbene, PPH3 that reacts with 2 Ar lithium. So, this is this dichlorocarbene that reacts with 2 Ar lithium, giving aryl chloride, and 2 lithium chloride gives this osmium Ar PH3 chloride CO, where Ar equals orthotoluene. So, what one sees that this dichlorocarbene complex when treated with aryl chloride gives the carbine complex. Here too, what one finds that this is a strategy that employs the earlier method of constructing the transition metal carbine complex on a transition metal carbene complex. So, this reaction is in tune with the other earlier examples that we have discussed at the beginning of this lecture. And this is a one that acts highly reactive dichlorocarbene species with aryl lithium. Transition metal carbine complexes, we have reviewed some of the methods which are used for preparing these complexes. Now, as for the characterization of these carbine complexes are concerned, they are mainly done by various spectroscopic techniques, as we had seen in case of the carbenes like NMR, proton and carbon NMR. So on and so forth, as well as by single crystal X-ray diffraction studies. as with the most of the characterization methods, X-ray being extremely extremely powerful. This has also been used successfully in stabilizing or structurally characterizing many such carbine complexes to gain insight into the nature of bonding that exists between the metal carbine complexes. So, here is a structurally characterized example of a chromium carbine complex. Where this metal carbine carbon bond is very short at about 169 picometer, whereas this chromium carbonyl carbon is very long as compared to this at 195 picometer. So, what is striking is over here that metal C carbine bond length is shorter than metal C CO bond length. The other which is the fallout of sp nature hybridization of the carbon, the metal Cr bond is nearly linear. In this case, the chromium C methyl angle is approximately 180 degree centigrade, and sometimes it may so happen that for certain metal carbine complexes this MCr bond may not be linear, but that is not due to other reason, but for the fact that many intermolecular interactions like packing effects are sometimes responsible for such deformation observed metal carbine alkyl bond angle. So, with that, let me conclude what we have discussed in today's lecture. We started off by looking at various synthetic preparative methods that were available for synthesizing these important metal carbine complexes, and these methods most of them or probably all but one of them involved synthesizing this carbine fragment on from metal carbene fragment. So, all of this method that we have been looked at involved the initiating species as metal carbene, on which by applying certain strategies like alpha deprotonation, alpha elimination as well as treatment with Lewis acids, as well as by nucleophile like phenyl-lithium, one could generate this metal carbine complexes. We have also seen that other than this generation of preparation of carbine from metal carbene fragment, the only other method that directly prepares metal carbine fragment by other routes involves this metathesis approach, where metal bond when treated with alkyne results in metal carbine complexes. We have incidentally what is kind of coincidental is the fact that Fischer prepared not only his method for not only his carbene complexes, but could successfully develop method for preparing the corresponding Fischer carbine complexes. Similarly, drawing the analogy, Schrock not only could come up with synthesis of a method for Schrock carbine complexes, but also could extend the method to prepare his own Schrock carbine complexes. So, these two people developed their own metal carbon double bond as well as metal carbon triple bond routes, and like in metal carbene case, metal carbine compounds are also have been characterized or can be characterized with various spectroscopic techniques including X-ray, and we have looked at one such structural characteristic example of chromium tetracarbonyl methyl carbine and iodide, where we saw that transition metal carbine bond is even shorter than transition metal carbonyl moiety, and that the angle at carbine carbon is linear owing to sp hybridized nature of the carbonic carbon moiety. So, with this I would like to conclude today's lecture, and in next lecture I am going to take up the characterization of transition metal carbine complexes in more details and their corresponding reactivity and property study. We are going to look at the orbital interaction involved between the carbine moiety and the transition metal in these complexes in the next lecture. So, till then goodbye, and I look forward to being with you in the next lecture. Thank you.